I want to do an example of using conservation of momentum to solve a problem in 2 dimensions. Conservation of momentum is one of my favorite topics in physics because, first of all, it's a deep, important part of how the universe works. But on top of that, it's a tremendously powerful tool for analyzing situations where you've got some clearly defined before and after in a situation, and you don't really care about all the details of what happened in between. So here's the problem I want to look at for this example. Batman sees his partner Robin has been locked into a cabinet that's rolling on frictionless wheels, and the cabinet is rolling toward a pit of fire. Robin has been locked here by the Joker or something and is plunging towards certain death. Batman leaps into action, quite literally. He takes a running leap, hurls himself toward the cabinet, swings around it, and jets off in a different direction before eventually landing back on the ground. In this process, I'll specify that the cabinet with Robin in it was originally moving at 3 meters per second straight toward this pit of flame, and Batman's initial speed when he leaps at the cabinet is 6 meters per second at an angle 10 degrees down from this vertical direction in this picture. And when he swings around, he yanks himself around the cabinet hard enough that he swings out, moving 8 meters per second at an angle of 20 degrees the other way, as shown. So my question is, has Robin been saved? Has Batman caused this cabinet to change its direction, rolling on its frictionless wheels, enough to save Robin from his doom? And in particular, I want to know the final speed and direction of that cabinet. Okay, I've given some data here. Batman's mass, including his armor and everything, is 100 kilograms. Robin is a bit more of a scrawny teenager and is locked into this lightweight but strong metal cabinet, 80 kilograms there. And so that's our data that we want to work with. So to solve a problem like this, one of the first things we should always do is draw a picture. Well, I've done that for us just to save some time and to illustrate the setup of the problem. With the picture drawn, one of the important things we're going to need to do is choose a reference frame, define coordinates for this. And since Robin is moving due left in this picture, this is a top-down view. Since Robin's moving straight to the left, I'll choose some coordinates to line up with that. I'll choose my x direction to be to the right, and my y direction to be vertically upward, like that. These are the traditional xy coordinates, but it's important to specify that anyway, so we have that down. Now, when I set up this problem, one of the things I need to do is think about, can I use conservation of momentum? I've got the before and after, initial and final sort of situations in my head here, but I want to know, is this reasonable to use conservation of momentum there? For conservation of momentum to work, remember, we need to have an isolated system in some sense or other. This clearly is not floating in deep space, so it's not truly isolated, but those frictionless wheels on the cabinet mean that we're not worried about friction slowing things down in the middle of this interaction. Batman, I said, was leaping through the air, so he's not really touching anything other than the cabinet. If we can ignore air resistance, air friction along the way, that's helpful. And the key thing that really helps with all this is those are obviously approximations, but also it's a very rapid interaction. And so this looks to me like, at the very least, it certainly counts as a type of collision. So in this collision, because it's a collision, that means that the interaction between Batman and the cabinet is going to be much more intense and strong than external interactions. So external interactions are relatively weak compared to the internal ones. So you can't just say they're weak in general, but they're weak compared to the internal ones. So we can treat this as an isolated system, or at least a functionally isolated system during this interaction. Okay, so that's a justification for why I can use conservation of momentum in the first place. And the next thing I should do, I suppose, I've drawn a picture, I'd like to collect some data. I've already got this list of information here from the setup of the problem. Other things I suppose I should write down are things like the masses. We know that the mass of Batman was 100 kilograms, and the mass of the cabinet with Robin in it is 80 kilograms. And the other crucial thing to write down, since we know we're using conservation of momentum to solve this problem, we should write down the equation for conservation of momentum. In general, that equation is just that the total initial momentum should equal the total final momentum. I'm using subscripts to note those, of course, in the usual way that physics people do. So I've got that. And in our case, there are two objects moving independently before and after. So I'm going to write this down. I'm just going to expand this out a little. I'll have Batman's initial momentum plus the cabinet's initial momentum equals Batman's final momentum plus the cabinet's final momentum. There we have that. And looking at this, I guess none of these are things I know right now. I don't know those momenta right now. So that guides me directly to my next step. I want to know, do I know these momenta? Can I figure out what they are, symbolically or in numbers? And the answer, happily, is yeah, I can absolutely figure that out because I know the definition of momentum. For example, the momentum of the cabinet initially has to be the mass of the cabinet times the velocity of the cabinet initially. And I'm going to write this, so it's mass of the cabinet times, in column vector form, we've been using column vectors to represent our, once we have our vectors and components. In this form, I suppose it's moving directly to the left, which is our negative x direction. So I can say negative, and I'll put the cabinet initial magnitude up there, and not moving in y or z at all. So that's my initial momentum of the cabinet. It's in the negative x direction, and you can see that's going to be a positive number. I suppose I could write that if I wanted to be really careful about it. I could write it as minus mass of the cabinet times the cabinet initial inside the column vector form, like this. I could write it that way, or I could even write it out if I wanted to multiply it all out. I've left myself a little overlap here. Oops. The mass of the cabinet, we said, was 80 kilograms. V, the speed of this initially, where did I write down the initial speed? Did I not write down? Here it is. V initial is 3 meters per second. 3 times 80, that will be negative 240 kilogram meters per second in the x component, and zeros for y and z. So symbolically or in numbers and units, I've got the initial cabinet momentum written down. I can do the same thing for Batman. I can write down that Batman's initial momentum. Well, for Batman's initial momentum, I'm going to need an extra step, right? I've got the speed and direction, his initial speed and direction, but to be able to write a column vector, I can write mass times velocity, but I'm going to need a column vector for Batman's velocity. So let me do that. I've got Batman's initial velocity here drawn in, and the angle is given compared to vertical. I know that to figure out the components of a vector like this, what I need to do is find a right triangle whose hypotenuse is the vector and whose legs are parallel to the x and y axes, and z if I have a z, but this is all on a horizontal plane as far as we're concerned. So I'm just going to do that. This is already parallel to the y-axis. That was how I defined that direction. And so I can just take another line that was through the tail of the vector, something parallel to y. So I can go through the tip of the vector and draw a line parallel to the x-axis. If you can see that in, I've got my make it a little darker for you. I've got a right triangle now with that vector as my hypotenuse, and I've got my angle theta initial labeled. So all I have to do is say, hey, this is my x component, this is my y component side. Those are the sides I care about, and I'll be careful about plus and minus signs as I go, but I can then write down that, well, let me separate this out a little. I can write down that the velocity of Batman initially is, okay, let's look at what these components are. The x component of this vector is in the positive x direction. It's moving that way. So I always, when I'm doing this, I like to be careful about the plus and minus signs. I've drawn my right triangle. I've said this is the x component in the plus direction. The magnitude, the hypotenuse, is Batman's initial speed, v Batman initial magnitude, times, and then I need to figure out, is this side opposite or adjacent to the angle that I have labeled? In this case, it's opposite that angle, and so katoa, sine, corresponds to opposite, so this is times the sine of theta initial. Same idea for the y component. Here, I have, this is also the positive y direction, so positive v Batman initial, the magnitude, that's the length of the hypotenuse essentially, the magnitude of the vector, times, this is adjacent to theta initial, so that's cosine, so cosine of theta initial. And we've got no z motion in here. So I've got that expression for Batman's initial velocity. I went ahead and plugged in the numbers for this just to figure out what it looked like. I plug in that velocity, that initial speed of 6 meters per second. I guess this is equal to plus 6 meters per second times the sine of 10 degrees and plus 6 meters per second times the cosine of 10 degrees and 0. And if I plug in those numbers, rather than making you watch me plug this into a calculator, let me just look this up. When I looked up that initial velocity vector, I got, rounding things off, I got 1.042 meters per second. I'm keeping some extra significant figures here just to avoid rounding error. So I've got that. I've got, 5.909 meters per second and 0. So I found those components for the velocity of Batman initially. And I can do, once I have that velocity, then I can do the same thing I did over here and say, that means that the momentum of Batman initially is going to be, that initial momentum is going to be, I should write it down, mass of Batman times v Batman initial vector. And again, I could just multiply this out. I'm going to multiply by 100. This is easy since it's 100 kilograms. I chose the number to make my life easy. 100 kilograms, I just shift the decimal place over by a couple. That tells me that Batman's initial momentum is 104.2 kilogram meters per second and 590.9 kilogram meters per second and 0. So I have the initial momentum of both objects, of the cabinet with Robin in it and of Batman. If I really want to, I could even add these together. Oh, I didn't do that in advance. Maybe I don't want to do that to myself. I could find the total initial momentum if I wanted to by adding these two together. To be clear, I should have said this originally. The system that I've chosen to look at, the isolated system, is Batman and the cabinet with Robin in it. And it's isolated from the floor and all the other things going on. And we were isolated from gravity effectively for the brief moment of this collision because it's weaker than Batman's intense yank at the cabinet. So we've got these initial momenta. Let me just go through and quickly figure out the final momentum that Batman has. Yeah, I can erase this. Figure out the final momentum. Exactly the same methods here, so I'll try to move through it pretty quickly. Here I have the final velocity for Batman going up and to the left, and this is the directions compared to vertical again, so I can do a dashed line horizontally parallel to x for this. I've got a right triangle. That means I'll have an x component here and a y component over here. I can figure out those components for my final velocity. So v Batman final as a vector is going to be, the x component here is in the negative direction. That's going more left than right. So it's negative. Negative speed is magnitude of v Batman final times that x side is opposite my angle, so that's sine again. Sine of theta final. For y, I'm still going in the positive y direction. So plus the speed again, v Batman final times the y side is adjacent to theta final, so that's cosine based on my trig. And 0, of course, because still not moving vertically in this particular story. And again, I can go through the step. I can write that this is going to be equal to minus 8 meters per second times the sine of 20 degrees and plus 8 meters per second times the cosine of 20 degrees and 0. And this gives me, I can write down my, again, I'll pre-compute this, use my pre-calculated results, and I get negative 2.736 meters per second and positive 7.518 meters per second and 0. So that's Batman's final, that's Batman's final velocity. Double check the direction. It's sort of negative x, positive y, more y than x. That looks like my picture, so I like it. And so then I can work out Batman's final momentum. P Batman final is equal to mass of Batman times V Batman final vector. Vector signs match up. That's good. And again, I'm just going to write down, I guess mass of Batman is 100. I can just write down 100 kilograms. I can just write this down. Minus 273.6 kilogram meters per second plus 751.8 kilogram meters per second and 0. And finally, I have 3 out of the 4 momenta in my conservation momentum equation. I've got those 3 out of the 4, and so the good news is I can combine those together to solve for the one that I don't know. I want to know the final momentum of the cabinet with Robin in it. So let me solve for that. Algebraically, clearly I've been doing this with numbers instead of symbolically most of the way through. We're going to do this with numbers. It's sort of a pain otherwise. But algebraically, I'll find that the momentum of the cabinet after everything in the final situation is equal to the momentum of Batman initially. I'm just taking this equation and subtracting Batman's final momentum from both sides. So I take the initial total, momentum of Batman initially, plus momentum of the cabinet initially, minus momentum of Batman final. That's just doing algebra on this equation to solve for the one that I didn't know anymore. This is the only one whose value I still didn't know. I've solved for that. Well, I guess I can write this down. I know all these in components. So P Batman initial was 104.2 kilogram meters per second, 590.9 kilogram meters per second, 0, plus this one, P cabinet initial, is negative 240 kilogram meters per second, 0, 0, minus, and Batman's final momentum here, minus 273.6 kilogram meters per second, plus 751.8 kilogram meters per second, 0. All of that together, long list of things, gives me my final momentum for this. And let me write down an answer. Again, this is something where I would just need to plug this into a calculator at this point, component by component. 104 minus 240 is going to be about minus 236, minus a negative 273 will give me a positive something, positive 100 something, I guess. What I end up getting going through the components is, when I add it all together, I get 137.8 kilogram meters per second, and negative 590 plus 0 minus 750 is going to be negative 160.9 kilogram meters per second, and 0. There is my final momentum for the cabinet. Already, this tells me a lot about what my answer is going to be, because the momentum is in the direction of motion. I've got a positive x and a slightly larger negative y. I'm expecting this, in this picture, I guess, my final is going to be something like that. It's going to be down and to the right from there. I guess I should be moving over into erasing space there anyway. So let me actually draw that in. So I've got my final momentum vector that is turned up here. I've used all this. I can get rid of it. I've got my final momentum vector, and so let's look at this. I'm expecting this to point, yeah, kind of like this. P cabinet final looks like what I've got. Looks like what my result has given me. let's go through and figure out the velocity, since that's what we're asked to find. I know that since the momentum, the final momentum of the cabinet is mass of the cabinet times V cabinet final, that tells me then that V cabinet final is going to be equal to P cabinet final divided by that mass. Remember, you can divide vectors by scalars, by ordinary numbers, anytime you want. And so I'm just going to divide this, mass of the cabinet, to be clear. So I'm just going to divide these numbers by 80 kilograms, and that should come out fine. In components, I would say V cabinet final is equal to, and in components I've got 137.8 kilogram meters per second divided by 80 kilograms, and I've got negative 160.9 kilogram meters per second divided by 80 kilograms, and 0. And the good news there is that the kilograms cancels out top and bottom in each component. The components have to have the same units, so that's good. Cancels out top and bottom to leave me with just meters per second. The answer I get in the end, again, pre-computed this, 1.72 meters per second and negative 2.01 meters per second and 0. There is my final velocity for the cabinet. I've solved this. That's basically the whole problem right there. I was asked for the cabinet's final speed and direction, so I suppose I can put that in there. The final speed, V cabinet final magnitude, is just the square root of 1.72 meters per second squared plus negative 2.01 meters per second squared. Remember that when you square a negative number, it comes out positive. Nothing's ever going to be negative in this square root. And so that ends up being, I guess, approximately equal to, when I round it off, I get about 2.65, call it 2.6 meters per second as the speed, the final speed of this cabinet. And if I want to do the final angle, I guess it pays off to draw this a little bit bigger. I have this thing like this. Here's this. I know the two components, drawing an x and a y component parallel to the axes. I know that the two sides, this is 1.72 meters per second, and this is 2.01 meters per second. I'm not putting the minus in because I'm sort of looking at this as the length of the sides of this triangle. The minus is already built in. If this is my angle, theta cabinet, at the end, what's that look like? Well, the tangent of theta cabinet has to be opposite over adjacent, 1.72 meters per second divided by 2.01 meters per second. The units cancel, which is good. Tangent always has to come out unitless. The inside and outside of sine and cosine tangent exponentials always have to be unitless. So that's good. And when I figure this out then, theta c is equal to the inverse tangent of 1.72 over 2.01. That comes out to be about 40 degrees. So it's not quite 45 degrees. 45 would be if these were exactly equal. They're not. It's a little more y than x, so it's a little bit less than 45 degrees. 40 degrees is the angle that I'm going from vertical. And it looks like Robin has been saved, and we've solved the problem. Again, the way that we did this, the key idea came down to conservation of momentum. This idea that mass times velocity as a vector is crucial for solving problems like this. By knowing initial and final mass times velocity, we were able to solve for the one missing piece, Batman's final momentum. And from that, once we had, missing piece here, the cabinet's final momentum, we were able to solve for that and work our way down to finding the final velocity from that idea. So I like conservation of momentum. It's a great concept in general, and it's really cool for answering before and after problems for isolated systems.